Hello, I am Dr. Melissa Johansson, the Director of Geode-Energy Limited, and I'd like to present my talk that was given to the SPE Bangkok chapter on the 27th of May this year, and it is entitled The Reservoir Characterisation of Pinnacle Reefs of Malaysia, the Application of Imaging Tools. The agenda of the talk will look at modern-day pinnacle reefs in general, the modern-day Laconian pinnacle reefs and the subsurface facies of the Laconian pinnacle reefs, followed by the typical porosities found within the Laconian deposits and a conclusion. A pinnacle reef is a small isolated spire of rock where corals grow in isolation in some deep water settings. When we look at modern day examples of typical pinnacle reefs, we see a number of zonations. In the interior of the pinnacle reef, it is a quiescent lagoon comprising isolated patch reefs surrounded by ooid shoals and micritic muds, followed by the back reef characterized by in situ corals exhibiting a typical groove and spur structure, often submerged in fragmented corals from storm deposits. Adjacent to the back reef is the reef crest, where abundant corals live and grow, followed by the fore reef, which receives the onslaught of the wave activity and comprise hardy corals that can stand the pounding waves, and which slope down to the deep fore reef, where talus and plated corals thrive in the reduced light. Comparative facies diagrams of a generalized Caribbean reef illustrating the corresponding living and the fossil examples show the shapes of the corals along the pinnacle reef reflect the stability to water roughness or wave energy, with branching corals obviously only able to grow in low energy environments such as below wave base, and dendroid robust branching to domal corals able to withstand higher wave activity. If we look at the environment behind the back reef lagoon, this area is sheltered from the highest energy conditions. Globular, spur and groove corals grow forming baffle stones and float stones, and during storm events debris removed from the reef core is deposited in the back reef. These facies are a mix of rudstones to grainstones comprising broken reef material, shells and occasionally ooids, which form an inner fringe around the margin of the lagoon, with the dominant sediments being packstones and waxstones. If we look at an example of a Miocene Luconian mudstone with waxstone from the inner ramp, we interpret these as lagoonal sediments. Note the deformation around the calcrete nodule. If we look at the environment on the reef crest, we see high energy robust globular or dome bindstones, followed by branching and more delicate corals forming baffle, bind and framestones behind the protected crest towards the back of the reef. If we look at a Miocene peripheral packstone and grainstone, we see abundant corals and red algae, which form one of the major facies of this area, together with the globular bindstones observed at the reef crest. The fore reef is the site of the most active wave activity and a locality where the most robust corals grow. These corals form encrusting massive bindstones capable of withstanding the force of the waves in very shallow water. Here we show a Laconian Miocene coral framestone with the clear growth rings of the coral alongside a modern-day equivalent red coralline algae, which can be interpreted on the reef crests of the inner ramp beach barrier. A simplified geological model of a pinnacle reef illustrates the proportions of different organisms across the reef, with a high proportion of forams, a low proportion of algae and little to no coral in the lagoon, contrasting with a mix of coral, foram and algae of the reef crest, followed by an abundance of algae and a low proportion of forams and little to no coral in the fore reef. Using our knowledge of the modern-day pinnacle reefs, we can look at the Laconian pinnacle reef of Malaysia. The Laconian province of Malaysia is situated offshore Sarawak on the northwest coast of Borneo. In the subsurface there are between 200 to 250 carbonate buildups of the Miocene age, which account for between 40 to 70% of the country's total gas reserve. Using high-resolution seismic data, we can see the multiple highs forming an inter-platform bathymetry with over 1,000 metres of relief, and we can still see modern-day pinnacle growth in Malaysia offshore, and here is an example of the Sipadan Island. In terms of the geomorphology of a pinnacle reef, a simulation of the wind circulation in the mid-Miocene indicates a summer and winter monsoon orientated south-southeast, north-northwest, and this wind direction has a profound effect on the fetch direction of the waves and thus the geometry and the internal architecture of the coral reefs. If you look at the cross-section of a pinnacle reef in 2D seismic line, we can see the characteristic high and steep slopes of the geomorphological features. A resistivity image log through the section can be seen, and where the dark colours are conductive and the light colours are resistive, and these display a stacking pattern of layered resistive sedimentation overlying a sharp conductive base. A typical log through the Laconian shows a low gamma ray in track 1, high separation of the resistivity logs in track 3, and abundant meso-macro porosity from the NMR in track 6. Chaotically orientated dips at an angle of 20 degrees represent the crestal sigmoidal bedding, and fractures can be seen in place in track 8. In the facies log in track 13, with the pink floatstones coinciding with the more resistive image, and the orange facies interpreted as rudstones representing a medium resistivity, and the dark blue packstone grainstone and the turquoise waxstone packstones coincident with the more conductive image. And if we infer the resistivity is due to the hydrocarbon in place, this suggests a more favourable porosity and permeability are found in the reef crest facies. The control of the thickness and location of the reef crests is related to the sea level changes through time. The transgressive hemicycles are dominated by tidal flats or lagoonal facies, i.e. those facies formed by red algae, and forams with the highest mud content, lower porosity or higher conductivity, and the regressive facies depicted by high energy carbonates, i.e. facies with macroorganisms and high porosity and high resistivity. However, the main platform coral growth, i.e. the thickest facies intervals, occur during sea level high stand, and the major sea level low stand resulted in the exposure of the reefs and thus dissolution and karstification. The dominant rock type of bioclastic packstone is associated with high stand and characteristically have shallow marine fauna, low argillaceous material and high porosity. Large pores are biomoldic with vugs connected via the network of small-sized interparticle pores. The depositional model switches from transgressive to regressive, with the transgressive regime flooding more of the back reef and having more massive coral reefs on the reef crest, whereas during the regressive period there is a reduced back reef and exposed reef crest. Using this information, we can now look at the Laconian pinnacle facies. The facies of the carbonates is related to the evolution of the fossils, and during the Miocene there was a massive increase in coral reef growth, with large benthic flora giving rise to platy corals. The Laconian carbonate facies can be divided into 8 facies based on core, with F1 being coated grain packstone, floatstone, limestone, F2 being a massive coral lime packstone grainstone, F3 an oncolite lime grain dominated packstone, F4 a skeletal lime dolopackstone, F5 a platy coral lime mud dominated packstone, F6 a branching coral lime dominated pack grainstone, F7 a cross-bedded skeletal lime packstone, and F8 a biturbated carbonate mudstone, i.e. a chalk. If we look at the core, we see some of the important features of the 5 different facies identified. In A, we see the coated grain packstones. In B, we see the massive coral lime grainstones. In C, we see the oncolite lime grain dominated packstone. And in D, we see the skeletal lime packstone with some leaching. And in E, we see the plated corals of the lime mud dominated packstone. When we look at the image log in a greater detail on a 1 to 20 scale, distinctive facies can be identified and thus allow us to extrapolate from core to the whole logged interval. The NMR supports the image log by identifying macro, meso, micro porosity. An outcrop analogue of the offshore Miocene is the upper Oligocene or lower Miocene carbonate platforms of the Mangkalihat area, East Borneo in Kalimantan. In the picture in A, we see a simplified paleo reconstruction of the area, and in the photographs here from B to E, we see selected classic platform facies, from breccia facies to high energy coral boundstone to shallow low energy bioclastic packstone to deeper low energy lipodocyclina packstone. The porosity of the pinnacle reef facies is varied, contrasting between megascale karstic to moldic porosity. On the large scale is the karstic caves formed during the sea level low stand, and here you see the Jintum platform with the blue arrow marking the top of the heavily karstified lower carbonate sequence, i.e. the red reflector, and subsequent flooding, the black reflector. This boundary can be traced clearly between the turbinations across the whole mega platform. Meso and macroscale porosity can be observed by the naked eye in core and from the VUGs on the image logs and the extended histograms from the NMR. The visibility porosity of 10% is divided into multi-porosity 50%, followed by VUGgy porosity 20%, intraparticle porosity of 15%, interparticle porosity of 10%, and fracture porosity of 5%. When we look at the thin sections of the meso and macro porosity, we see the porosity in blue from the resin impregnation of the thin sections, and we see intraparticle and moldic porosity in A, in B fracture porosity, in C VUGgy porosity, and interparticle porosity in D. The fracture porosity is observed in many scales. Here it is seen on the resistivity image log in blue rectangular symbols dipping between 50 to 70 degrees and striking predominantly northeast-southwest, as well as in the thin section in the D with a tiny fault observed in the lower plate. In contrast to the larger scale porosity, microporosity is observed, and quantification of the microporosity indicates that the Miocene carbonates contain an appropriate amount of microporosity, which can be the sum of 40 to 50% of the total porosity. If bound water is retained in these micropores, the logs can often look water wet in an oil and gas rich zone. When we cross-plot porosity versus permeability and shade the facies, we see the best quality facies is the coral lime grainstone, and the worst being the coral lime mud to pack stone. However, there is a fairly poor grouping which suggests that an overprint of diagenetic control is in place. If we look at diagenesis, we see that micritization, cementation, and stylization are detrimental to porosity, with dissolution fabric and non-fabric selective, enhancing porosity. So to conclude, that the carbonate rocks in central Laconian offshore Sarawak, Malaysia consist dominantly of limestone with a minor constituent of dolomitic limestone and dolomite. The carbonate rocks consist of 5 facies, mainly coated grainstones, massive coral lime grainstones, oncolite lime grain dominated packstones, skeletal lime dolopackstones, and coral lime mud dominated packstones. Foraminifera, red algae and corals are the dominant components forming the carbonates. The diagenetic history revealed that the platform underwent the following diagenetic alterations: cementation, recrystallization, silicification, and dolomitization. Most of the original aragonite skeletons of corals either were dissolved or recrystallized to calcite. And the reservoir quality, and particularly the permeability of carbonate rock, is affected in most cases by micritization and calcite cement. Thank you.